Hi guys, hope all is well. So we're on lesson 3 and I'm going to start lesson 3 by showing you PowerPoint, which will help us fill in our notes after we're done watching it. So this is the objective that you can write down, that we're exploring our real number system and we're going to focus on whether a number is rational or irrational. So our real number system is divided into two categories, the rational numbers and the irrational numbers. It's just that we use rational numbers, it seems like very often, that they decided to classify them a little bit further. So there are subsets of the rational numbers. There are smaller boxes within the rational numbers. And those boxes, once pulled out, we can see are the integers, the whole numbers, and the counting numbers. So we're going to start with the smallest box. Our counting numbers is our smallest subset of the real number system. It's the first numbers that you ever started using. When we count, the numbers that we say are classified as the counting numbers. A more sophisticated name for counting numbers are natural numbers, so you should know that word also. But so we can show that our counting numbers are 1, 2, 3, and so on. You know, you can count forever. You don't ever have to stop counting. There are things that are going to get in our way in life that stop us, of course, but numbers go on forever. So the counting numbers do go forever in a positive direction. But just remember the things that we say when we count. Counting numbers fit inside of the whole numbers, which means that the whole numbers must have the numbers 1, 2, and 3 in them. There's just more that they have, and it's the number 0. That's the only extra thing that whole numbers have. That's the only difference between whole numbers and counting numbers. But now the whole numbers fit inside the integers, which mean that the integers must have these numbers 0, 1, 2, 3, and so on. But what else do they have? Oh, they have the -1, -2, -3, and so on. What we like to say is that the integers are the whole numbers and their opposites. So what the heck are rational numbers? I feel like I've talked about everything. Well, what about everything that comes in between, right? Those fractions and decimals. So that's what a rational number is. We like to say that numbers that can be written in the form of a over b, where a and b are integers, and b is not 0, because remember you can't divide by 0, that's what's classified as rational. Some people say that they like to just say, oh, if I write it as a fraction, it's rational. A very specific word that you should use, though, is that it can be written as a simple fraction, because by using that word simple, it means that a and b are integers. So if the rational numbers are numbers that can be written in the form of a over b, where a and b are integers, and we talk about the decimal form of that number, which means it's terminating or repeating, what the heck are irrational? Well, it's those crazy things. It's the numbers that can't be written as a fraction. That sounds crazy to me, right? What can't be written as a fraction is a famous number, right, pi. But there are so many other ones that we have already talked about. Certain square roots and certain cube roots are crazy. The decimal part goes on forever. We like to say that the decimal form of the number is a non-repeating and non-terminating decimal. So let's try and classify some numbers. So 0.5, you know you can write it as a half, therefore it's rational. 7/10, it's already written as a fraction, therefore it's rational. What about the square root of 25? So let's calculate that. The square root of 25 is 5. 5 is a counting number. Counting numbers are in this box of rational numbers, right? We said that rational numbers can be written as a fraction. Can't we write 5 as 5 over 1? We can. So that's why the square root of 25 is considered a rational number. So if we're going to be talking about square roots and cube roots, let's take a look at our list of perfect squares and perfect cubes. So you can always refer back to this. If we look at the square root of 25, I could see that in my list of perfect squares is the number 25, and it's the 5th number down, and that's why the square root of 25 is 5. So what about the square root of 7? Well, 7 is not in my list of perfect squares. It comes somewhere in between, so it's one of those crazy decimals. It's irrational. 0.22222 ... that means that it's a repeating decimal, All repeating decimals can be written as fractions. I'll tell you that 0.2 repeating is 2/9. If you don't believe me, pull out your calculator, do 2 divided by 9, and you'll get 0.2 repeating. So it's rational. But this, it's not repeating, and it's going on forever. It's one of these crazy decimals. It's irrational. -2, oh, that's an integer, right? It's the opposite of 2. So it can be written as a fraction. It's rational. The cubed root of 27. Remember when you see that little 3, it's a cubed root. So look through your list of perfect cubes. Oh, the cube root of 27 is 3. It's rational. What about the cube root of 5? Oh no, 5's not in this list. That's a crazy decimal. It's irrational. 0.3 repeating. That decimal, that fraction you should know. 0.3 repeating is one of our more famous repeating decimals. 0.3 repeating you should know as the fraction 1/3. Therefore, it's rational. 0 is a whole number, so it's rational. Pi, that's a famous irrational number. 2 to the 3rd power. Calculate it. 2 times 2 is 4. 4 times 2 is 8. 8 is a counting number, therefore it's rational. Square root 50. Look through your list of perfect squares. Oh no, it's awful close to 7, but it's something in between, so it's irrational. What about the cubed root of 8? Look through your perfect cubes. Oh, there's 8. The cube root of 8 is 2. It's rational. 3.14. Did you get fooled? This is a rational number. This is not pi. Pi is crazy, goes on forever. This doesn't go on forever. This is 3 and 14/100ths. This is rational. Be careful. We do use 3.14 as an estimate for pi, but it is not pi. -2.69358 ... Crazy decimal going on forever. That is irrational. So now we're going to go to our lesson. Hopefully you already wrote down the objective, and we don't have to do this now. And we're going to fill in the notes for the counting numbers. So counting numbers, we can write it in set notation like how I did in the PowerPoint. It's the numbers 1, 2, 3, and so on. It's numbers we use when we count. Whole numbers, remember, are the counting numbers with one extra element of 0. Integers, we can write this in words. We could say it's the whole numbers and their opposites. We could write it in set notation. Start with a ... End with a ... Rational numbers, we can't really write in set notation because there's so many in-betweens, but we can say can be written as a simple fraction. Let's also write down what we see in its decimal form. The decimal form is terminating or repeating decimals. And an irrational cannot be written as a simple fraction. And the decimal form, they're non-repeating and non-terminating decimals. So let's fill in this Venn diagram. It's like the boxes that I had in the PowerPoint. So this whole thing is our real number system, divided into two groups. Remember, the rational or the irrational. Remember that smallest box was our counting numbers, sometimes called natural numbers. The next box out of that were the whole numbers. Remember, the whole numbers just have one more element of 0. The next one out of that were our integers. And the next one out of that, it's our rational numbers, which I already called it. And now this is just what we did in the PowerPoint, but now we have a record of it. So we're going to classify it as rational or irrational, and we will explain. And if it's rational, we have to state all subcategories of the rational numbers that it belongs to. So you'll also tell me if it's counting, whole, integer, and it says show your work when necessary. So this is a terminating decimal, therefore it's rational. And we have to give a reason. Its reason is because it can be written as a fraction. I'll even write as 12 over 100, right? 12 hundredths can be written as 12 over 100. I can simplify that. 6 over 50, right? So it is a simple fraction. And there aren't any other categories it belongs to, because remember, the fractions and decimals are just rational. But -4, we'll classify it as rational, can be written as a fraction, as -4 over 1. And if we talk about its subcategories, it's also an integer. 5 1/4. I'm going to come over to the because for a second, and I'm going to change that to an improper fraction. It can be written as 21 over 4. So that makes it rational. And it doesn't have any other subcategories. It really is just rational, but this is a fraction. So that's why we called it rational. 0 is rational because it can be written as 0 over 1. It's a whole number. It's also an integer. Square root of 25 calculates to be 5. Therefore, we can write it as 5 over 1. So since it can be written as a fraction, it's called rational. It does have subcategories, a lot of them. 5 is a counting number. And remember, the counting numbers are in the whole numbers. Remember, the whole numbers are in the integers. So when it says list all subcategories, make sure you refer back to this diagram. If you find the smallest box it fits in, then it fits in everything on its way out. I know I keep on saying boxes and these look like circles, but you get what I'm saying. 2/3 is already a fraction, so it's rational because it's a simple fraction. The cubed root of 8 is 2. Can be written as 2 over 1. Therefore, it's a simple fraction. Which makes it rational. And then the square root of 7, it's crazy. It's irrational. Can't be written as a fraction. We could also say its decimal is non-repeating, non-terminating. How do we prove that this can be written as a simple fraction? I have to tell you that um, I don't really require you to know how to do this algebraically in 8th grade, but you can see that there's this algebraic way of changing all repeating decimals into fractions. Um, I'm going to tell you kind of like a little trick, and then when you're in high school, you'll probably learn better uh, how to change a repeating decimal into a fraction. The steps really are here. If you want to look through it, if you want to ask us any questions about it, we'll explain how this really works. But really, when you have a single number repeating, the trick is you take that number and put it over 9. It's that denominator of 9 that causes a remainder that's always the same. If I were to change this fraction into a decimal using longhand division, you can see what I'm talking about. 9 goes into 22 times. 2 times 9 is 18. I have a remainder of 2, so I have to put a 0, bring it down. I got a 20 again. 9 goes into 22 times. 2 times 9 is 18. And this is going to keep on happening. So it's that denominator of 9 that causes you to get the same remainder all the time. Now this, number 10, has 2 digits repeating. So I have to write those 2 digits down, but now I can't just put a 9 here. Now I have to put a 99. And you could even check this out on a calculator. On my calculator, I could do 45 divided by 99. And you see I get 0.45 repeating. Now in number 11, there's 3 digits repeating. So what do you think I put in the denominator now? Hopefully you notice the pattern. It is 999. Take a look, 125 divided by 999. And there we go. And when you have a whole number, like before the decimal, that's your whole number in front of the fraction. So since 0.5 was repeating, we write it as 5/9. I just want to point something out to you on your calculator so that I know you know how to use your calculator properly. If I do 5 divided by 9 on my calculator, look what I get. And some people tell me, oh, Miss Sands, that's not 0.5 repeating because there's a 6 at the end. It's impossible for you to have so many 5s and magically get a 6 at the end. Your calculator is so smart that since it can't fit the whole number, it knows rounding rules. It knows that if you have 5 or higher, you round up. So it eventually rounded since it can't fit it. So you have to be careful. If you see the same number listed and then the last one is one higher, you need to recognize that as your calculator rounding. It really is 0.5 repeating. Is the square root of 8 rational or irrational? It happens to be irrational because if we look at our list of perfect squares, it's not there. Thus, I will say that the square root of 8 is between the square root of 4 and the square root of 9, right? The square root of 4 is 2, and the square root of 9 is 3. So the square root of 8 is between the whole numbers 2 and 3. The square root of 8 is between 2 and 3. The decimal is non-repeating, non-terminating. The square root of 4. Well, the square root of 4 equals 2, and 2 can be written as 2 over 1. It's a simple fraction. Therefore, it's rational. And that's what you have to do for homework. Notice that you do have to give the subsets, like what we did over here. Here I wrote that it was counting whole and integer because this was equal to 5. So make sure you're telling me what subsets it belongs to. And enjoy the rest of your day. See you. Bye.